Second, determine if the polynomial splits into linear terms, factors. It might be that this is not possible, but it will certainly be possible under the complex numbers. So if it's possible under the real numbers, then we will be dealing in a situation that is like this one. If it splits only into the complex numbers, then we will be dealing in a situation related to this. Once we determine this, then we check for the following condition, which is associated with this. Determine if for each eigenspace E lambda, the dimension of E lambda is equal to the algebraic multiplicity of lambda. Now, if one of these conditions fails, well, the matrix is not subject to the diagonalization process. So what can we do? And what is the diagonal associated? Well, it turns out that it comes from here. Why? To find the matrix that transform A into a diagonal matrix, we will do this. Each of these sets that we have here contains vectors in the associated spaces, right? Well, once we collect them, we have a set of vectors. Well, from that set of vectors that we have, we're going to form a matrix. Form a matrix by adjoining or appending the columns of the vectors in the set S1 union S2 union Sk. Well, and call this matrix S. Then S inverse AS is a diagonal matrix with the following characteristics. It looks like this. It looks like lambda 1, lambda 1, lambda 2, lambda 2, lambda k, lambda k, 0, 0. Now, how many times does this repeat? Well, as many times as the algebraic multiplicity of lambda 1. How many times does this pattern repeat? Well, as many times as the multiplicity of lambda 2. And so on until we find the last one, who says, well, how many times do I see the copies of lambda k here in this diagonal matrix? Well, as many times as you see members of this element here. So, well, with this we conclude the topic on diagonal matrices.